This video is about upward moving projectiles. So this is in the vein of kinematic equations, same basic concept. It has time, position, velocity, and acceleration. So if we look at a projectile being thrown upward, let's just take a look at those variables. So the origin, it's going to be at the starting position of the object. Now everything will be on the y-axis because it's moving up and down. Let me move this out of the way. There we go. And these kind of problems are broken up into two different parts: the projectile moving up and the projectile moving down. These two parts basically mirror each other. We'll get into this a little bit later. Now let's take a look at what this means for the for the variables as the projectile is moving up. So we're just looking at the first part, from the moment he releases it to the moment it gets to the peak. So v0y, that's the velocity of the object the instant it is first thrown upward. v0y will be positive because it is moving in the positive direction. vfy is the velocity at the peak, or when we're just looking at it moving up to the peak. The velocity the instant the projectile reaches the peak will be 0 meters per second. It's at rest for a split second once it gets to the peak. AY, that's the acceleration of the object as it is moving upward. So it is slowing down, so the acceleration will be in the opposite direction of the velocity. AY is going to be negative. The acceleration for all objects on Earth, we use negative 10 meters per second squared. Gravity is what causes the acceleration. Now, delta T, we're just looking at the time interval it takes for the projectile to reach the peak. Now, notice delta T doesn't have a direction, right? So if you look at the equations over here, it does not have a direction. Delta y is the final position. It's a positive number because it's ending above the origin. So it will be positive because the final position is above the initial position. So the first thing that we did was we did a lab. It's called the bouncy ball lab, in which you dropped a bouncy ball, it bounced up, and we were measuring the height. So this is what we did, right? So we dropped the ball from the top of a meter stick, and we record the bounce height in centimeters. We ran the trial 3 times and found the average. So using this, we're going to find the time that it takes to get to the peak. So you can see in this scenario, I dropped the ball from 1 meter up, it bounced up 60 centimeters, and I converted it to 0.6 meters. Now, before we get to this, I want to find the time that it took to get from the table, the first bounce, to the peak, and then eventually to the peak back down. Same principles for projectiles. It says drop projectiles, upward projectiles. What 3 variables are being asked to find? What 3 variables do you already know? Which equation has those 4 variables? So this is the original question. How is an object being thrown upwards similar to an object falling down? So let's just take a look at this. So the object as it's moving upward, well, the acceleration is going to be negative because gravity is pulling it down. Gravity is what's causing it. Now the velocity as it's moving upward is going to be positive. The velocity, that final velocity when it gets to the peak, is going to be 0. Now the displacement is going to be positive. So now I can calculate the time that it takes to get from the ground to the peak. Well, let's take a look at it moving back down. So you can see here the acceleration is still negative, right? The initial velocity, though, is 0. This is just a dropped projectile. Now, the final velocity as it's moving down is going to be positive, and the displacement, well, it's falling the same distance that it went up. And then this will give me the time it takes to get from the peak to the ground. Now, these times are going to be the same. The time that it takes to get to the ground from the peak and the time that it takes to get from the peak to the ground are going to be the same. So let's do this problem. A ball bounces straight up and reaches a height of 0.6 meters. What was the object's velocity when it was initially bounced? How much time did the object take to get to the peak of the arc? What was the total time the object was in the air? With what velocity did the object land? So let's just find that first part, right? Let's just find that initial velocity. So I know the final velocity at the peak is 0, and the displacement, well, that's how high it went above the table, 0.6 meters. So I plug everything that I know into the equation, and I'm looking for the equation that has these 4 variables, or the one that doesn't have delta t. That's going to be the last one. So I plug everything that I know into the equation, and I solve for the initial velocity, and I get 3.464 meters per second. Well, now I can solve for the time interval. Now, I can use any of these 3 equations. It doesn't matter. If I calculated the initial velocity incorrectly, I'm going to get the time interval incorrect. So I'm just going to use the top one because it's easier, and I'm going to get the time 0.3464 seconds. So the next thing says, what is the total time the object was in the air? All I have to do is double that, right? 0.3464 seconds, I double that. That'll be the total time. Now, the velocity that the object lands, well, as soon as it hits that first bounce, it's going to move upward at 3.464 meters per second. It's going to hit the table on that second bounce, going down negative 3.464 meters per second. They're virtually mirror of each other. So that was the question. How could the total time the ball is in the air from the first bounce to the second bounce be found? Explain your answer. Well, just double the time that it takes to get from that first bounce to the peak, because they're mirror images. It's going to take the same time to get from the peak back down to the ground. And now we went a little more into detail with the upward projectile simulation. So now we simulated it, and we launched a projectile up in the air. We measured the time it took to get to the peak and the displacement. How high did that object go? All right, so when graphing the time to the peak versus the initial velocity, is the line linear exponential? So you can see here that is going to be the blue line. It's going to be linear. Which kinematic equation does the line represent? So how you find this one is, what you do is you look at the equations that are known. So you know the acceleration, that doesn't change. You know the final velocity at the peak is 0, that doesn't change. Then you have two variables, right? You're changing the initial velocity and it's affecting the time to the peak. So you're looking for the one with out displacement. So this one is going to, well, it's graphing that first kinematic equation. Next one is saying when graphing displacement versus initial velocity is a line linear exponential. It's going to be an exponential curve. And which kinematic equation does this line represent? It's going to be the last one, because I need the one that doesn't have time, right? Because we already know the acceleration, the final velocity, the initial velocity, and it's graphing the displacement. All right, so the last part was looking at these problems. When graphing an object's position versus time, what does the slope of the line represent? It's going to be the velocity, and you can see that the slope is not linear, right? It's not linear, it's curving. When graphing an object's velocity versus time, what does the slope of the line represent? The slope of the line represents the acceleration, and you can see that this line is linear. When graphing an object's acceleration versus time, what does the slope of the line represent? You can see down here, the slope of the line, I mean, it's horizontal. And look at the velocity versus time graph. So this part was just asking what part is of the velocity graph, this middle graph, which part is when the velocity is positive, when it's 0, when is it negative. The velocity is going to be positive as it's moving upward. The velocity is going to be 0 as it reaches that the peak, and it's going to be negative as it moves down. When a projectile is being thrown upward, does the acceleration change? The answer is no, right? The acceleration doesn't change. Explain why or why not. Gravity is what's causing the acceleration. The gravity, what the force pulling on, the net force is not changing on this object as it's moving up and coming back down. So now let's take a look at the graphs of this, right? So this was the position versus time graph. The slope of the line represents the velocity. So you can see that it's getting to a peak and then it's coming back down. Notice they're mirror images of each other. So now let's take a look at the velocity versus time graph. If I were to graph the slope of my position versus time, this would be that graph. Notice it's positive as its object's moving up, it's negative as it's moving down, and it crosses that line, the horizontal axis at the peak. And my acceleration is going to be the same. It's going to be 0, or no, negative, right? Negative 9.8 or negative 10, depending on what you use. All right, so let's just go over some problems that you can have with projectiles being thrown upward. An object is thrown straight up with a speed of 5 meters per second. How much time did the object take to get to the peak of the arc? What was the object's displacement to the peak of the arc? What was the total time the object was in the air? With what velocity did the object land? Okay, a lot to take in here. But the time interval, right, that's what we're going to solve for first. That's what it's asking. I plug everything that I know in. So we're looking for the peak. We know the final velocity is 0. It says speed of 5 meters per second. Speed is a scalar quantity. which means that it does have a direction, but it's starting to move upward. So the initial velocity is going to be 5 meters per second. I look for the equation that has all four of these variables. It's going to be that top one. I plug everything in and I solve for the time interval. I get half a second. So now I can solve the displacement. Now I can use any three of these equations. The last one would be better because if I miscalculated the time, I can still get that displacement correct. I'm just going to use the third one just because it's easier. If I wanted to double check, I could use that fourth one, 1.25 meters. Now, the next question it asks, what's the total time the object was in the air? If it takes a half a second to go up, it's going to take half a second to come back down. The total time the object was in the air was a second, right? And then it says, with what velocity did the object land? 5 meters per second up. Well, it's going to land 5 meters per second down, negative 5 meters per second. So here's a known height, right? And I go over why this is a special case. An object is thrown straight up and reaches a height of 30 meters. What was the object's velocity when it was initially thrown? How much time did the object take to get to the peak of the arc? What was the total time the object was in the air? With what velocity did the object land? So I'm looking for the initial velocity first. I know the final velocity at the peak is 0. I know the displacement. It says height, 30 meters, but remember, because the final position is above the where it originally started, the displacement is going to be positive. Then I look for the equation that has all four of these variables. It's that bottom one. I plug everything in and I solve for the initial velocity. Now, then I can solve for the time it takes to get to the peak. Now, here's why it's a special case. Initial velocity is in all of these equations. If you messed up the initial velocity, you are not going to get the time correct. It does not matter what equation you use at this point. Either you're going to get the same answer, right? So you plug everything in. I just use the top one because it's easier. It's going to take 2.45 seconds to go to the peak. The next question is, what is the total time the object was in the air? Well, I take 2.45. If it takes 2.45 seconds to go up, it's going to take 2.45 seconds to come down. So the total time, I just double that, right? It's going to be 4.9 seconds. And the velocity, well, it goes up to 24.5 meters per second. It's going to land, going down negative 24.5 meters per second. All right, last question. An object is thrown straight up, reaches the peak in 5 seconds. What was the object's velocity when it was initially thrown? What was the object's displacement to the peak of the arc? What was the total time the object was in the air? With what velocity did the object land? All right, a lot of questions in here, but let's just take it one step at a time. The first thing it's asking us to find is that initial velocity. I know the peak, or no, I know the velocity at the peak of the arc. It's going to be 0. I know the time interval is in the equation or in the problem. Then I'm looking for the equation that has these four variables. It's going to be the top one. I plug everything in, solve for the initial velocity. And like I said, this is a special case because if you do not calculate the initial velocity correct, you will not calculate anything else correct after that because initial velocity is in all of them. So I'm going to solve for the displacement. Doesn't matter which one I use. I'm just going to use the easiest one. Plug everything in, 125 meters. So the next thing says, well, what's the total time the object was in the air? Well, if it takes 5 seconds to go up, it's going to take 5 seconds to come back down. So it'll be in the air a total of 10 seconds. And the velocity that object lands, if it goes up 50 meters per second, it's going to land negative 50 meters per second. How fast do you have to get to the moon, right? So now we're talking about going up and not coming back down, going to another object. So if you were to take like a rifle and like fire it directly up, yeah, the wind is going to affect it. The actual height wouldn't really go too high. Like this is the fastest moving, one of the fastest moving like macro objects that are available with the rifle. Without air resistance, though, it will continue going up, up, up past the square, and eventually, well, it will come back down eventually. Now, if you go scale up even higher with the railgun, right? So railgun is electromagnetic pulse, and it launches a huge slug going like hypersonic speed. I mean, we're talking like 7 times the speed of sound. If you were to launch it up, the actual height of a railgun, it wouldn't go too. Air resistance would still slow it down. Without air resistance, though, I mean, you could almost hit the Hubble Space Telescope. Now, if you were to fire the enhanced hypervelocity launcher, this is something that like governments use to test the hulls of spacecrafts because orbital velocity is very fast. It's like 17, 18,000 miles per hour, and they need to test like what would happen if a spaceship hit something going that fast. So essentially you launch this thing and it vaporizes thing, but it does go about 10 miles per second, incredibly fast. Now the actual projectile would vaporize, but even if it were not, like if you did the math, right, the simple math, the calculated height would go there, right, without any air resistance it would go there, come back down. But like I said, there is a catch, because we did get far enough away from Earth for the lower gravity to take effect. So that brings us to escape velocity. So escape velocity is the minimum speed needed for a free non-propelled object to escape from the gravitational influence of the mass of a body. That is, to achieve an infinite distance from it. So the escape velocity from Earth is 25,031 miles per hour, so about 11.19 kilometers per second. That's over 30 times the speed of sound. So when we fire like a rifle bullet directly up, well, a rifle bullet only goes 1.42 kilometers per second. Yeah, that's pretty fast. Even with that, even without an atmosphere, would not be able to escape Earth's gravity. Now the railgun has a velocity of 3.50 kilometers per second. Even without an atmosphere, there'd be no way for it to escape Earth's gravity. And that enhanced hypervelocity launcher projectile has a velocity of 16 kilometers per second. So yes, if Earth did not have an atmosphere, theoretically that would hit the moon, right? But this just shows you how fast those rockets have to go in order to get to orbital velocity and eventually leave. Like the men that walked on the moon, they had to go this fast to escape the Earth's gravitational pull. So just remember, as a final thought, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.